So this is a perpetual motion machine of type 1. So we'll see PMM1 and 2 for first and second laws. Then we'll talk about first law applied to open systems or flow process. So for example, you look into nozzle, turbine, pump, etc. And we'll talk about, we'll derive general equation for mass and energy balance. Okay, so this all is covered in your syllabus for this chapter. Finally, we'll go to some practical devices like turbine compressor, and we'll do steady state analysis. So steady means that it is not changing with time. Okay, so these are the devices we are going to look into. We'll apply or demonstrate the use of first law in these devices, and we'll also do some transient analysis where the system is changing with time, tank filling and emptying. This is what we are going to look into. Let us now go to the first law, or let us take an overview. Okay, so the first law is basically a law of conservation of energy. It says that total energy of an isolated system is constant, or energy cannot be created or destroyed. Okay, it can be transformed from one form to another. So that is, I believe you all have studied in physics. So the same things, the same principle or the same logic we apply in thermodynamics. We will talk about thermodynamic systems and we'll see how this energy conservation is applicable or how this is applied. Okay, and we also discuss something called mechanical equivalence of work and heat, how they are equivalent and how to consider them in a cycle. Let us first begin with Joule's experiment. Okay, so this is historically one of the most important experiments done for this subject. So this is the set of experiments which formed the basis of first law, or they have actually demonstrated that heat and work are equivalent. These concepts seem very obvious to us, and these are the very basic things. But back then, let's say in 1850s, around that time when these experiments were done, there was not so much clarity. Okay, so this is what made us clear that heat and work are equivalent. Can you people hear me?
Yes,
Yes,
sir.
sir.
Okay, fine, fine. Okay, so what we do here is that what Joule did was that he had a system. Okay, let us say this is a closed box. But you see the dotted line, this is the system. So there's a box which is closed and which is insulated. So this hashed area that you see, this is insulated. So basically I have an insulated system, but we can do some work transfer. Okay, heat transfer is not allowed. We are doing work transfer using this. So this is called tidal wheel. Okay, so this is, you can assume something like a fan which is inserted in this system. So what happens is if it rotates, when it rotates, it will generate work. Work is done because the liquid is opposing. Work is done against friction. Okay, so we can do work on the system by rotating the system. That is what we are going to see. So how do we do work? You see a weight here. So let us say this is a weight of mass m which is held here. So this is called state 1. State 1 we have temperature 1 and the mass is at this location. Now I allow this mass to fall. So it will fall for some distance. Okay, let us say z. It comes down. While coming down, it rotates. So this is a pulley which is connected to it. It comes down. The pulley is pulling this thread, which is again connected to the steerer. Okay, so it is a very simple system. Mass is falling down and it is rotating this steerer. So once it does that, what will happen is work will be done, which is equal to the difference in potential energy or mgz. Okay. Now the temperature changes from T1 to T2. So which will be higher, T1 or T2?
T2.
T2.
Yes. So,
Sir.
yes.
T2.
So yes, one person has said, then it's enough. If you are not understanding, then you ask. Otherwise, if the first person says is correct, then we'll move ahead. So what we see in this experiment is that we have a system, we do some work on that system, and the temperature is changing. We are going from state 1 to state 2. Okay. Now I want to come back. How can I go from 2 to 1? I can remove heat, right? So for removing heat, what I can do is I can take the whole system, I can remove the insulation and dip it in a water bath or any other liquid which will take out heat. Okay. So if you dip it like this, then after some time it will come back to T1 again. Right? No, nothing complicated here. The system is just cooling down because we removed the insulation. Okay. So now what we see is we have started with T1, state 1, we went to state 2 and come back to state 1. Okay, so we can say that we have completed a cycle. So let us have a look on this cycle. So we went from 1 to 2 by work
Sir,
input. Yes.
how we have come from 2 to 1, from state 2 to state 1?
So state 2 is basically your temperature is higher or temperature has changed. So we just removed some heat. So I dipped this system inside a water bath or any other cooling liquid. I dipped the system. I removed, you see, here we have insulation. So heat loss cannot happen. That insulation is removed and the system is inside water body, water bath. So that cools down. That's all. So from 1 to 2, the difference is okay, let me go back. So from 1 to 2, the only difference is that the temperature is changing. Okay, because of that, some system properties may change, but it is a closed system. So no other change in system, only whatever change is there that has to be accounted using this temperature change. It is basically getting heated up. Work is getting converted to heat. That's all we'll discuss in detail. So that's what we are bringing back. So once you are basically heated it, you cool it down, it is back to the original state or initial state, right? So you'll see this in this diagram. So let us say we plot this cycle in some general coordinates x and y. These are thermodynamic coordinates. It could be pressure, temperature, anything. The plot will vary according to what variables you are plotting. So let us just keep it simple and general. We'll say that x and y coordinates are there. This is state 1 and this is state 2. So work transfer changes from 1 to 2. Okay, it could be any arbitrary path. We'll not worry about which path is there. We'll keep it general. So the system goes from 1 to 2 because of work input at this to the system. Okay, because of the steerer wheel. Now I want to bring it back from 2 to 1. So I will remove the heat, what we have seen in the last slide. So now the system is restored to the initial conditions. Okay, now let us, what Joule observed was, Joule did these experiments many times, repeated using different liquids, different masses of that block, different cooling liquids. But for all the experiments, what Joule observed was that this work is always directly proportional to heat. How much heat has to be removed to go back to state 1. Okay, if you remove more heat, you will go to some other state. If you remove less heat, you will go to some other state. So the exact amount of heat that has to be removed to reach back to state 1 is proportional to how much work has been done. Okay, so this has been observed experimentally by Joules. Now, what he further did was that, let us say that here we talked about only one work input and one heat loss. Let us say we have a cycle with more than one work. So there could be 2-3 times where you do work or 4-5 times where you take out heat. So when you talk about such a cycle, even if you sum over all the work done during the cycle, that will still be proportional to the total heat interaction for that cycle. Heat transfer during the cycle. Is this clear? Any questions on this? I'm just saying that the total work done on this cycle is proportional to the total heat that needs to be removed from the cycle to go back to the initial state. Any questions on this, or this is clear to everyone? Okay,
Yes, sir.
fine. So what Joule did was that he proposed the constant of proportionality. Okay, because this is proportional to this. So let me say I will want to put equality sign. So he said that let W equal to J times summation of Q in the cycle. Okay, so this was one of the major results which came from Joule's experiment, and this J is Joule's equivalent or mechanical equivalent of heat. So now you see we are equating work with heat. This is something which is previously not known. Now when we study this subject, this is a very obvious result for us, but it was not so obvious 100 years ago. So this was the major achievement or accomplishment of Joule's experiments, that they were able to equate work and heat. Okay. Now Joule actually published a paper called mechanical equivalent of heat, in which he gave this value for that J. Okay. What is the value or amount of work required to produce a unit of heat? Okay. So what he did was work generated by friction, what we discussed, by that pedal wheel. Okay. So he provided the value of J. He said that if you take 1 pound of water, so these are not SI systems. Okay. Pound, Fahrenheit. So he's saying that if you take 1 pound of water and heat it by 1 degree Fahrenheit, so for that, this is the amount of work that is required. So he said that for 1 calorie of heat to the system, you need 4.15 joule. Whatever the liquid you take, whatever the mass you take, which if you design a system bigger or smaller, he repeated his experiment several times, but he always came up with this value. Okay. Now, for this equation, this is what Joule proposed. So Joule said J is equal to 4.155 joule per calorie, where the unit of work is measured in joules and Q was measured in calories. Okay, so these are not SI systems. In SI units, we say Q is also in calories, joules. Okay, so when you specify work and heat both in joules, so you get J is equal to 1. Okay, so this constant of proportionality will be 1 if you are taking both in SI units. Is this clear, or any question on this?
Sir, is this valid for a cycle only?
Right now we're talking about a cycle. It is valid for process also.
Sir, but in
We'll
process, there will be change in internal energy also.
that we are coming to. Internal energy we have not defined till now. That we are going to define.
Okay, sir.
So for okay, right, you are correct. So this is true for a cycle only. Okay, for if you talk about a process, then we need to talk about internal energy. Let us first talk about the cycle. So cycle means I have come back to the initial point, and then the total work done during the cycle is equal to total heat that is released in that cycle, and this will be one for both in joules SI units. Okay, is this clear? For a cycle, is it correct? The person who asked the question. You
Yes,
are
sir.
okay?
Yes, sir. Yes, sir.
Fine. Now let us. So I can also write it this as a cyclic integral. Okay, I can write it in summation form, or I can write it as a cyclic integral. For a cycle, dw is equal to dq, and both are inexact differential. These are path functions. Okay, so that's why I've written d slash q. Now this is what we call as first law of thermodynamics. This is one of the forms. We'll see there are different forms in which we can express the first law. This is one of the forms, and these are like one of the historically important forms. This is what Joule derived. Joule said that for a cycle, dW is equal to dq. Okay, so this can be termed as a first law for a closed system undergoing a cycle. And basically, this is conservation of energy. It says how much work you have supplied to the system, the same amount of heat you have to remove from the system to go back to the initial state. That's all. Now, now we'll talk about internal energy. Okay, so let us talk about a process. What happens in a process? Let's say that initially we have a system which has some internal energy. Basically, we'll refer to this as total energy of E1. Okay, now this is interesting, or this you have to be very careful. So when we say heat, okay, we always say heat is at the boundary. The system is supplied Q amount of heat. We never say that the system contains Q heat. Okay, that is a wrong statement. But internal energy is what is contained in the system. I can say that the system has E1 of energy. What energy is there, that we'll talk in this and next slide. But this is right to say that the system contains this energy, but I cannot say the system contains Q. I cannot say the system contains Q amount of heat. Heat is always the energy which is seen at the boundary. So Q amount of heat is getting supplied, but the system contains E1 amount of total energy or E2 amount of energy. Is this clear to everyone? Okay.
Yes, sir.
Fine. So what we see here is that we added some heat. So the heat addition will increase this energy, right? If you are holding the system, let us say if I hold this piston, so all the heat that is supplied will go to increase the temperature or increase E1, right? Now, if you do some work, if you move the piston, so some work is done by using this energy, right? Where that energy is coming from? By using this energy or using what was supplied. So heat addition will increase the energy of the system, while work done will decrease the energy of the system. This is a very common observation for any system. I'm using piston cylinder as an example, but for any system, heat addition will increase the internal energy and work done will decrease it. Okay.
Sir, what if we compress the system? Means we do work on the system. Then the
Then you
internal
will
energy should increase.
correct. So work done by the system will decrease if you replace work done to the system. Let me write it down. So this is the work done by the system. Okay, that is decreasing the energy. What you said is work done. It will be to the
On
system.
the system.
On the system. Yes. Yeah, that is for correct. Work done on the system will increase. Is it okay?
Yes, sir.
Your voice is true. So how do I find what is the energy E1? So I'll say that Q minus W is equal to delta E. How much energy has changed from 1 to 2? Okay. Now E is the total energy of the system. Okay, we'll see in the next slide how much what are the parameters that it considers. But let us say that E is the total energy of the system. So I can write first law in this form. I can say heat supplied is equal to work done plus whatever the change in internal or total energy is there. So this is first law of a closed system undergoing a change in state. Okay, so this is not for a cycle, this is for one process where system is changing from E1 to E2. We can actually integrate it and do it for a cycle also, but for a single process, this is how first law can be represented. Okay, so let us look at this energy. whether it is a system path process or path function or point function. So let us say we have a cycle where we have path A and path 2. There could be different work and heat interaction. So that if you go back to this equation, so this is the equation we will try to explore. So the heat supplied for this path Q will be equal to what is the total work done during that path plus what is the delta E, what is the change of internal energy from point 1 to point 2. Right? These all are path dependent. Similarly, I can do the same equation for path B. I can say the heat supplied for path B is equal to work done plus delta E. Right? If I add all this, it becomes a cycle. Right? A and B, two paths are forming a cycle. So if I add Q for path A and path B, it becomes Q for a cycle. So I have written it wrong. Let me correct it. So it will be like this. Q is equal to okay. So heat supplied to the system is equal to total work done plus delta E in the cycle. Everyone is okay with this equation?
Yes, sir.
Yes, sir.
Yes, sir.
Now, in the previous slides, what we have seen? We have seen that this will be equal to this, right? Summation of Q one cycle is equal to W, summation of W in that cycle. This is what we have derived in Joule's experiment, right? So if I remove these two terms, I will be remaining term will be delta E cycle is equal to 0, right? Or I can say delta E for a cyclic integral is D is 0, right? Now this happens for a point function, which shows that D will not be path dependent. It is a point function and it is a property of the system. Okay. So now let us look at what are the factors or what are the parameters that are considered for this. So E is the total energy of the system that we are talking about, and it is a sum of kinetic energy, potential energy, and U. U is internal energy. Okay. So these two terms are macroscopic, and this is microscopic. This is basically the energy contained in the molecules because of translation, rotation, and all that. So for most of the examples that we'll consider in this course, we'll see that kinetic and potential energy will be 0. So it is a system at rest, and let us say at the height is also 0. That is the reference height. So we'll say that E is equal to U. These terms are removed. So E is equal to internal energy. Most of the time when we talk about first law, and what we see is that this U, internal energy, is a function of temperature only. Okay, it will not depend on pressure, volume, or any other parameter. It is a function of temperature only. So mostly when we talk about conservation of energy or first law, we'll say that E is equal to U. This is what we are going to consider, and then this, instead of D, I will add du, and then we'll work on the first law. Okay, is this clear to everyone? Any questions on this? Fine, I will move ahead.
Sir,
Yes.
how can we define absolute potential energy without a reference?
When did I say absolute? Okay, so this is basically referring to the system. If your system is moving, we consider a stationary system, then we'll say that, okay, stationary system with reference to some reference coordinates. Then we'll say that potential energy is 0.
Okay, sir.
Fine, system at rest with respect to Earth or something like that. Generally, most of the examples that we'll see will have a stationary system which is not moving. So in that case, this is the only parameter that we are concerned with, internal energy. Okay. So let me, okay, just give me a minute. I will be back. Hello. Yeah. Is this slide clear?
Yes, sir.
Yes, sir.
Okay. Now let us look at how we can express the first law. So we have written Q is equal to W plus delta E. So that we can write in differential form also. So Q we can write delta Q, del Q and all that. Now when we what we have discussed in the last slide, when we see that total energy is basically your internal energy, so I can write instead of E, I will be mostly referring to du. Okay, so for if you look at the example numericals for this chapter, we'll mostly talk about du. Unless otherwise stated, you will take des du. And we can also write this in intensive form. So, okay, this is not correct actually. I need to write it like this. So these are all in exact differentials, right? So I missed this anyway, I'll do the corrections. So work is also in exact. So this is exact because this is a property of the system and it is a point function. So d is correct, du is correct, but work and heat we have to write it like this. Okay. So these are the different forms of first law of thermodynamics. Okay, these are the same statement for the same law. There's no difference, only we are writing in different forms. So this is the form which we will mostly use. Or we can write that in intensive form also. dq is equal to dw plus du. When we talk about extensive or intensive terms. And mostly we will be dealing with displacement work, which is called PDV work. So instead of dw, I can write PDV here. Okay, so these are the different forms in which you can express the first law, and different equations will be used for different numericals based on what is the given parameter, or whether you want to talk in terms of intensive as or extensive properties. So let us now look about heat. So this is what we have discussed in the last class. Okay, we have looked into constant volume and constant pressure processes, and we have defined heat transfer. We have calculated using CV and CP, right? So specific heat at constant volume, CV, it can be referred to this change of internal energy U per unit time. So how, sorry, per unit temperature. How this U changes with temperature when your volume is constant. Okay, and hence we can integrate and we can write that delta U, or change in internal energy, is the integral of CV into dt. Okay, is this clear? Any questions? Till
Sir,
now?
why is that partial differential?
Okay, because you can. Okay, that's a good question. You will use a function of t only. Okay, we will look into other forms also. So just to keep it general, we have kept it in this form. So let me stop. So I will